Okay, we begin another series of lessons. In this case, we'll be dealing with systems of equations and inequalities. This would be equivalent to our Chapter 3 in our college algebra course. And these will be, again, abbreviated lessons, a little bit shorter than what normally I would give in the classroom. So let's look at the scenarios that you can have. And we are going to focus in the case where you have the same number of equations as you have variables. So if you have a system of two equations with two variables, say x and y. So here we're talking about linear systems where the graphs of these equations would be lines. That is, if you have two variables. And the scenarios that you could have when you graph two lines, the lines can either intersect at one point, like I have in this first diagram here. So in that case, we'll have one solution. We say the system is consistent, and of course the lines intersect. If the lines are parallel, there's no intersection point, so there's no solution. We say the system is inconsistent. And if you have, say, two identical equations, they're going to produce the same graph. So we're going to say the system is consistent. The lines are coincident. They coincide. In that case, you're going to have an infinite solution set. So in the note here, I have for a system of equations with one solution, the equations are independent. For a system of equations where the lines are coincident, that is, they coincide, the equations are dependent. Now, normally in our course, we give about 4 or 5 different methods for solving basically the same problem. Okay. Elimination and substitution are just two of the methods that we have. We have some methods involving matrices, determinants, and a few others. The focus here is going to be on elimination and substitution. And I do have a video where I show you how to solve systems on the TI-83 graphing calculator. So if you have some online assignments that are, say, multiple choice where you don't have to show your work, you can easily solve a lot of these problems on your graphing calculator very easily. So we're going to do the first one by the elimination method, sometimes called the addition elimination method. So we start with, say, a system of two equations with two variables. And the object is to basically use your properties of equality. That is, we're allowed, if you have two things that are equal, you're allowed to multiply both sides by a non-zero number, and you still maintain equality. You can add corresponding sides of two quantities that are equal. You have two equations, okay? So the object is to perform one of these operations so that we eliminate one of the variables. So we want to add the two equations so that one of the variables cancels. And if it helps to multiply one of the equations by a number or both equations by a number, we do this. So in this first one I have 2x minus y is equal to 3, and 5x plus 4y is equal to 40. So the objective is to eliminate one of the variables by adding. Okay. So notice in this case, if I add the x and the y, are not going to cancel. So what I do, say, okay, let's multiply the first equation by, say, 4. So if I multiply the first equation by 4, this gives me 8x. This becomes 8x minus 4y is equal to 12. Now if I add, I get 8x and 5x gives me 13x. Minus 4y and 4y cancel. And then over here, this will be 12 and 40 will be 52. So by multiplying the first equation by 4 and then adding, I've canceled the y variable. So I get one equation with one variable, which is fairly easy to solve. We just isolate the variable. So in this case, I just divide both sides by 13. 52 divided by 13 gives me 4. So I get x is equal to 4. Now to get the value of the y, I could go ahead and eliminate the x and solve for y, but since I know the value of x is equal to 4, just plug it into either one of these equations. Okay, I'm going to put it into the first one. I'll put it 4 where the x is here. 2 times 4 is 8. Bring the 8 over here. That's 8. 3 minus 8 is minus 5, so I get minus y is equal to minus 5. Negatives cancel out, and I get y equal 5. Okay, so the solution is x equal to 4 go to 5. Okay, that's the elimination method. Now to solve the same problem using substitution, what we have to do is we want to solve one of these equations for one of the variables, either x or y. It's more convenient to solve for y. Bring the y over here, the 3 over, so the first equation becomes y is equal to 2x minus 3y. So in this case, I eliminate one of the variables by substitution. So I use this substitution here in the second equation, and so where I have a y, I put 2x minus 3. So that eliminates the y. So I get 5x plus 4 times 2x minus 3. And then I go ahead and multiply. I get 8x minus 12. So 5x and 8x is 13x. Take the minus 12 over to the other side. We get 40 and 12 is 52. 13 into 52 is 4. And then put a 4 over here in the first equation. 2 times 4 is 8. Minus 3 is equal to 5. I get the same answer. So you have x equal to 4, y is equal to 5. So if I were to graph these two equations, they would intersect at the point in the rectangular coordinate system at the point 4, 5. Okay. Now the next one, solve the system of equations, and I have 3x plus y is equal to 10, 9x plus 3y is equal to 13. So again, I'm going to multiply the first equation. Okay, I want to cancel the y. It doesn't matter which variable, but I'm going to cancel the y. So I'm going to multiply the first equation by negative 3 all the way across, and then add. So this will become a negative 9x. This will become a minus 3y. This will become a minus 30. Okay, and then we just add those. So minus 9x and 9x cancel. Minus 3y and 3y cancel. That is, we get 0. So the left side becomes 0 is equal to, and then on the right side, negative 3 times 10 is negative 30, and 13 is a negative 17. Now whenever you're solving a system of equations, doesn't matter what method you're using, and you come up with a contradiction like this, 0 cannot equal to negative 17. Okay, this one has no solution. Okay, empty set, so it has no solution. And this would be the scenario where the two lines, if you were to graph them, the two lines would be parallel, no point of intersection. Okay, that's what we get. Let's clear this. Okay, the next one. Solve the system. So again, I'm going to eliminate the x, say by multiplying the first equation by minus 3. So notice this will be a negative 3x, a negative 3y, and a negative 3. So if I add the corresponding sides, I'll simply get 0 is equal to 0. Okay, that's a true statement. But I have no variables left over here, so I don't get an x equal to a value or a y equal to a value. So, and this is a scenario where we have an infinite solution. That is, the lines coincide, so there's many points of intersection. So in this type of a scenario, it's actually the same line. Notice if I divide the second equation by 3, I get x plus y is equal to 1, so I get the first one. So they're identical. Okay. So all the points on that line are the solutions to the system. So the way we could write this in a solution set is we could write it. We could solve the first equation for y or x. It doesn't really matter. You get y is equal to 1 minus x, and we could say the solution then is y equal to 1 minus x, where x is any number. So replace the x by any number and you get different solutions. Okay, or we can write this as a solution set like this: set of all x, y, such that y is equal to 1 minus x. And this is where x belongs to R. That is, x is any real number. Okay, that's one way to do it. Now I want to point out that the three scenarios that I just went over, where you have one solution, no solution, or an infinite solution set, will be the same scenarios if you have, say, 3 equations with 3 variables, or 4 equations with 4 variables. The only difference is you're not going to have lines. Okay, in the scenario where you have 3 variables, you're going to have planes, but you could have the same scenarios. You either have one solution, no solution, or an infinite solution set. Now, with the case where you have no solution is probably one of the easiest cases, because there you just stop and you say no solution. If you have obviously unique solutions, and you got to find the value for x, for y, and for z if you have 3 variables. In the scenario where you have an infinite solution set, you have to express the solution usually in terms of one of the variables, either x or y. Okay, so I could have also written this as an ordered pair, say x and 1 minus x, and then you let x be any number. So you pick any value for x and plug it into this ordered pair here, and you get different solutions. Now, and the last problem that I'm going to look at, we have a system of equations where we have 3 variables, 3 equations and 3 variables. Okay, so in this particular case, what you're going to have is, well, in the case where we have the 2 equations and the 2 variables, we used elimination or substitution to reduce it to one equation. Well, in the case where you have 3 equations, you try to reduce this down to 2 equations with 2 variables, and then you do the same thing as I did in the previous ones. Now, I did the first one by substitution and by elimination. Usually if you have the variables all on one side, the convenient way to solve it is by elimination. Okay, so that's what I've been using in these. Okay, so basically what you want to do is you can take the first equation and the second equation and then eliminate one of the variables. It doesn't really matter which, x, y, or z, take your choice, and then take the second and the third equation and eliminate the same variable. Okay, so in other words, you don't want to eliminate the z between the first and the second, and then the y over here in the second and third, because then you're going to have the predicament where, again, you're going to have 3 variables. So take the first and the second, and then the second and the third, or the first and the third, as long as you take 2 different ones. Okay, so here's what we're going to do. I went ahead and I took the first equation and the second equation. Now again, I want to point out, if there's fractions involved, To simplify it, just multiply the equation that has the fractions by the LCD, and that'll clear the fractions, and then you just follow the procedure I've been using. Okay, so I'm going to multiply, I'm going to use this first and the second and eliminate the z. Second here, and eliminate the z. So I'm going to multiply the second one by -4 all the way across. Okay, so it could be -4 times 2x is minus 8x, and then 1x is minus 7x. That's how I get this minus 7x over here. Then minus 4 times y is a minus 4y, and a minus 3y is a minus 7y. I get this here. Okay, then minus 4 times 3 is -12, and 19 is 7. Okay. Then I'm going to take the second and the third. Okay, second and the third, and I'm going to multiply by 3. So I'm going to multiply the second equation by 3 and then add to the third to cancel the z. Okay, so here's what I have. 3 times 2x is 6x, and a minus 2 is 4x. 3 times y is 3y, and 3y is 6y. And then 3 times z is 3z, and minus 3z cancels. And 3 times 3 is 9, and a minus 17 is a minus 8. So I get this equation right here. So now I've reduced the 3 by 3 to a 2 by 2. Okay, 2 equations with the 2 variables. And I could work it from there, but it's always easier to simplify if possible. So notice the first equation, they all have 7s in it, so you can reduce it. The second equation, you can divide by 2. You have all even coefficients there. So that's what I did in the next one. Okay, so in the next one, I divided the first equation by -7. Let me clear this here. Divided the first equation by -7, and I get this: x plus y is equal to -1. And then the second one, again, I don't have to do this, but it just makes it easier to work with. Divide every component by 2. I divide 4x by 2, I get 2x. 6y by 2, I get 3y. Minus 8 by 2, I get -4. Okay, so I get this. So now I have it. Two equations with 2 variables. So using again the elimination method, I'm going to eliminate the y. So I'm going to multiply the first equation by -3. So -3 times x is -3, and a 2x is a minus x. Minus 3 times y is minus 3y, and 3y cancels. Minus 3 times a -1 is a positive 3, and a -4 is a -1. Divide 2 by the negative, so I get x is equal to 1. X is equal to 1. Okay, so now I can go to either one of these two right here and replace the x by 1. Okay, put a 1 right there. X plus y is equal to -1, so put a 1 there and take the 1 over. I get -1 minus 1. That's -2. So I get y is equal to -2. Okay, now I need my z. So I have to go to the original one. Okay, and I put a 1, and again you can pick either one of these 3. I'm going to pick the second one because it's the coefficient of the z is 1, so it's easy to plug in. So put a 1 right there where the x is, that's 2. Put a -2 where the y is. Okay, that's 2 minus 2, that cancels. I get z is equal to 3. So I get x equal to 1, y is equal to -2, and z is equal to 3. You can write it out this way, or in solution form you can have this way as an ordered triplet. That's your solution. Okay, now I will put a link on this video also in case you want to check out the one where I solved problems like this using the TI-83 plus graphing calculator. So check that out if you want, and I'll be back with another video. So please subscribe to the channel. We'll see you next time.